Hello, let's see you again. And I want to invite you to our avionics engineering lecture. Okay, so nice. Let's start our lecture number 8. The topic, optical gyroscope. You know, optical gyroscopes, such as the ring, laser gyro, and the fiber optic gyro, measure angular rate of rotation by sensing the resulting difference in the transit time for laser light waves traveling around a closed path in the opposite direction. This time difference is proportional to the input rotation rate, and the effect is known as the Sagnac effect. After the French physicist Georges Sagnac, who in fact demonstrated that rotation rate could be sensed optically with the Sagnac interferometer as long ago as 1913. And this figure illustrates schematically the basic configurations of the Sagnac interferometer. The Sagnac effect time difference, delta T, between the clockwise and anti-clockwise path is given by this simple equation. Delta T proportional 4A over C squared times theta dot. Here A is the area enclosed by the closed path. C, the velocity of light, and theta dot, the angular rate of rotation about an axis normal to the plane of the closed path. The difference in optical path length, delta L, equal C times delta T. Or we may rewrite delta L proportional for A over C times theta dot. So the difference with delta T over, in first case, we have a C squared. In this case, for delta L, only C. Okay? A rigorous derivation of the above formula requires the use of the general theory of relativity. A simple kinematic explanation, however, will be given a bit later for the case of a circular path in vacuum. Referring to this figure, consider a photon of light starting from P and traveling around the perimeter in a clockwise direction, and a photon starting from P traveling in the anti-clockwise direction. In the absence of an input rate, the transit times of the two photons will be identical and equal to 2 pi r over c. It must be equals t. Now, consider the path rotating at a rate theta dot. In time t, P has moved to P straight, right? And the path length for the clockwise photon is equal to the 2 pi times r plus r theta dot times t. And the path length for the anti-clockwise photon is equal next expression. We have only difference between the sign. In first case, we have a positive and this negative sign, okay? The difference in transit time, delta T proportional, and we have two difference between that. This one over the C and minus this one over the C. Substituting as a t proportional to pi r over c, the yield as a delta t will be proportional 4 pi r squared over c squared times theta dot. And delta L will be simplified in this case, as you remember, without only c squared transform is simply as c. A will be proportional to pi r squared, and hence this formula and this formula are identical with two previous ones in previous slide, right? It can be shown that these formulas are unchanged when the optical path comprises a medium of refractive index n, such as when an optical fiber provides the closed path. The Sagnac effect is very small for low rates of rotation. Michelson and Gale in 1925 used a Sagnac interferometer with a rectangular cavity 600 meters up to 330 meters to measure the Earth's rotation rate and measured a path difference of only 1/4 fringe. The invention of the laser in 1960 radically changed the situation and enabled optical gyroscope based on the Sagnac effect to be developed by exploiting the laser's ability to provide a source of highly coherent light with very stable wavelength characteristics. The first experimental ring laser gyro was demonstrated in the US by Masek and Tevis in 1963 and has since been developed by a number of companies and establishments worldwide to large-scale production status. Many tens of thousands of RLGs are operating in a strapped-down ENS, inertial navigation system, and have established high accuracy with better than 0.01 degrees per hour bias uncertainty, and MTBF is excess of 60,000 hours. The RLG is described in the next section of today's lecture and is basically an active resonance system with the laser cavity forming the closed optical path. Input rotation rates are measured by the difference in the resonant frequencies of the clockwise and anti-clockwise path resulting from the difference in the path length produced by the rotation. The development of the Lovelock single-mode optical fiber in the early 1970s for the telecommunication industry enabled Sagnac effect fiber optic gyros to be developed. These use an external laser diode source together with suitable beam splitting optics to launch the laser light so that it travels in clockwise and anti-clockwise directions through a cylindrical coil comprising many turns of optical fibers. The active area of the closed optical path is thus multiplied by the number of turns in the coil. Path lengths of hundreds of meters are achievable. The first FOG was demonstrated in the US by Valley and Schotil in 1976. Development and production of the passive interferometer type of FOG or IFOG has since taken place in many companies and establishments worldwide. The IFOG operates basically as a Sagnac interferometer and measures the phase shift in the fringe pattern produced by the input rotating ray. The accurate measurement of very small Sagnac phase shifts has required the development of special techniques which will be explained. The IFOG was initially developed to an AH RS level of accuracy. And the first large production orders, the IFOG-based AHRS, were placed in 1991. Development to inertial accuracy has since taken place in many organizations, and IFOG-based IN systems are now available. The resonance type of the fiber optic gyro, the RFOG, operates in a similar manner to the RLG, but with the resonant ring of optical fiber, given by an external laser diode. Two acousto-optical modulators are used to shift the laser frequency injected into the clockwise and anti-clockwise path, respectively, with the modulation frequencies being controlled by servo loop to maintain the resonance peak condition. The difference in the resonant frequencies of the two paths is then directly proportional to the input rotation rate, as with the RLG. Development of the RFOG appears to be on the back burner at the present time, as the IFOG type is given an excellent all-round performance. Attention has thus been concentrating on the RLG and the IFOG. The basic elements of the RLG, ring laser gyro, are shown schematically in the next picture. The two counter-rotating laser beams are generated from the lasing action of a helium-9 gas discharged within the optical cavity. The triangular closed path being formed by reflecting mirrors at each corner of the triangle. This closed path forms the resonance cavity, and the longitudinal model frequency F is determined by the cavity optical path length L, being given by F proportional of NC over L, where N is an integer and C the velocity of the light, right? Okay. At zero input rotation rate, the clockwise and anti-clockwise path length are equal, and there is zero difference between the frequencies of the clockwise and anti-clockwise waves. When the RLG is rotated about an axis normal to the plane of the closed path, there is a difference in the path length of the clockwise and anti-clockwise traveling waves. As shown earlier, which causes a frequency difference between the two waves. This frequency difference is measured by allowing a small percentage of the two laser beams to be transmitted through one of the mirrors. A corner prism is generally used to reflect one of the beams so that it can be combined with the other to generate a fringe pattern at the readout detector photodiode. An input rotation rate causes the fringe pattern to move relative to the readout photodiode at a rate and in a direction proportional to the frequency difference, no matter as positive or negative. A sinusoidal output signal is generated by each fringe as it passes by the photodiode. These are spaced so that there is a 90 degree phase difference between their output, so that the direction of rotation can be determined from which photodiode output is leading. The photodiode outputs are then converted into the positive or negative, right, pulses by suitable pulse triggering and direction logic signals. The frequency difference delta F, resulting from a difference in optical path length delta L, is given by the first expression on this part. And from the equation, we can get the delta L proportional, our classical, we already remember, for A over C times theta dot. Whence delta F will be proportional, the same expression as you can see, only we have F in here in the iPad and L here. So the wavelength of the laser transition lambda proportional C over F. And hence, delta F will be equal 4A over lambda L times theta dot. In other say, delta F simply equals chi K sub naught times theta dot. K naught here is a gyro scale factor. It's equal 4A over lambda L. The gyro thus behaves as an integrating rate gyro, and we can see here, integrate from 0 to t delta F to delta t will behave as a constant K naught, and integral from 0 to theta d theta. The angle tuned also about the gyro input axis in the time period t capital here is equal to the net number of positive or certainly negative pulses counted in that period. The RLG thus provides a direct digital output of the input angular rotation with a process of inherent integration carried out in the optical domain. The high sensitivity of the RLG can be seen from the following example. A typical RLG with an equilateral triangular cavity of perimeter L equals, suppose, 0.2 meters or 20 centimeters. Has an area in this case 1.9245 times 10 in power minus 3 square meter or 19.245 square centimeter. And laser transition wavelength lambda equals 0.633 micron or 0.633 times in 10 in power minus 6 meter. In this case, the RLG scale factor is scatters this expression and finally get these values 60,825 hertz per radian per second. And hence, we can say that one pulse is count 1 over this value radian, and that get us 3.39 arc seconds. So this resolution can be increased by a factor of 4 by triggering on the positive and negative going zero crossing of both directors. And alternative and equally valid explanation of the RLG, which some some of you may prefer, is as follows. The two counter-propagating waves set up by the laser in action will beat together and set up a standing wave pattern in the cavity. This standing wave pattern remains fixed in space irrespective to the angular rotation of the cavity. An observer rotating with the cavity, in this case, the readout photodiodes will thus see a succession of light and dark fringes as the readout moves past the spatially fixed standing wave. And this figure illustrates the principle. The RLG behaves in an analogous way to an incremental optical encoder with the encoder shaft angle fixed in space and so measures the angle through which the gyro has been rotated. The fact that the standing wave pattern remains fixed in space as the cavity rotates can be interpreted as a manifestation of the inertia, which electromagnetic energy processes in view of its mass equivalent. This figure illustrates the construction of a typical RLG. The equivalent triangular cavity is machined from a solid block of a vitroceramic material known as a cervite, which has a very low coefficient of thermal expansion. The three mirrors are mounted on the block by optical contact for stability and ruggedness. The mirrors have multi-dielectric coatings and have a reflectivity of more than 99.9%. The mirror system being a critical area of the RLG technology. Absorption and above all scattering must be minimized. The optical path length of the cavity is adjusted by means of a piezoelectric transducer attached to one of the cavity mirrors. The position of the mirror being controlled by a servo loop so that the laser oscillates at its peak average power. High voltages of the order of 2000 volts DC are applied between the two separate anodes and the common cathode to ionize the helium-neon gas mixture and provide the required lasing action. The system uses a common cathode and two separate anodes so that Langmuir flow effects in each plasma arm are cancelled out by control currents, which balance the currents in the two discharges. Okay, nice. These flow effects can cause bias shifts due to the differential changes in the refractive index of the light, traveling along the clockwise and anti-clockwise paths. A major problem which has had to be overcome with the RLG is the phenomenon known as a lock-in. This arises because of imperfections in the lasing cavity, mainly in the mirror, which produce backscattering of one beam into the other. The resulting coupling action tends to pull the frequencies of the two beams together at low rotation rate, producing a scale factor effect. For input rates below, a threshold known as the lock-in rate, the two beams lock together at the same frequency, so that there is zero output and dead zone result. On the figure A on the left part of this slide, illustrates the effect of locking under steady input rate conditions. This locking dead zone is of the order of 0.01 to 0.1 degrees per second, compared with 0.01 degrees per hour accuracy required for an INS. A very effective method of overcoming this problem is to mechanically die the laser block about the input axis at a typical frequency of about 100 Hz, with a peak velocity of about 100 degrees per second, corresponding to an amplitude of 1.5 arc seconds approximately. The amplitude of the theta rate and acceleration are chosen, and so that the dwell time in the lock-in zone is so short that lock-in cannot occur. On the right side of this slide, this figure illustrates the effect of DISA on removing the dead zone. The DISA signal can be removed from the output by mounting the readout reflector prism on the gyro case and the readout photodiodes on the block, so as to produce an optical cancellation of the DISA signal. Alternatively, the readout prism and readout photodiodes can both be mounted on the block, and the unwanted DISA signal can be removed by a digital filter. Some reduction in gyro bandwidth is encouraged, however, because of the digital filter response. Alternative solid-state techniques are also employed to overcome locking. The mechanical diesel technique, however, is by far the most widely used technique at the current time. Also, a criticism could be made in terms of technical elegance of a solid-state system, which depends on mechanical diesel. The fact that zero failures in the diesel system is over several hundred million hours have been experienced. This slide is a photograph of a current widely used inertial quality ring laser gyro and shows the glowing laser beams in the optical cavity. The photograph, by courtesy of Honeywell, is of the Honeywell GG1320AM digital laser gyro. This gyro is used in Honeywell Air Data Inertial Reference System, ADIRS, installed in many civil airplanes. It is also used in the INS systems Honeywell produced for military aircraft. A slightly lower accuracy version of the GG1320 AM digital laser gyro is also used in what is termed a super AHRS, RLG performance characteristics. Only some of them will be mentioned. The general performance characteristics of a ring laser gyro are summarized as high accuracy. In this case, the RLG meets the dynamic range for a pure IM system of being able to measure angular rate from 0.01 degrees per hour to 400 degrees per second to the required accuracy or dynamic range of 10 in power 8 over 1. Intensivity to acceleration. In this case, the RLG has no acceleration sensitive bias error, as it is based on optical effects rather than inertial effects. Very high rate range. This is limited only by noise bandwidth characteristics of the readout electronics and equals plus minus 1000 degrees per second is no problem. Very high scale factor accuracy. In this case, errors are in the 5 to 10 ppm bracket. Negligible warp up time. It means the full gyro operating from the instant of turn on. Next characteristic, excellent turn on and turn on performance. Performance capabilities can be maintained over several years without calibration. And that's one of the best characteristics. Random noise uncertainty. This measured in degree per square root from hour and is one of the RLG's most important error characteristics. The error is significantly higher than experienced with angular momentum gyros. It affects the system heating determination in the gyro compassing phase during the initial alignment process. This is because it extends the time required to filter the Earth's rate signal from the gyro noise in order to determine the initial heating. Next characteristic, very high reliability. Its MTBF is access of 60,000 hours are being demonstrated in large-scale surveys. Then, 100,000 hours MTBF is being approached. Why? This is the laser beam ultimately destroys the mirror, but this is over a very long period. The light equivalent of to over 100 years. The usage is being played. But I never listen to any aircraft, even automobile, near the term of 100 years. And last characteristics, volume. This is determined by the path length, typically 20 centimeters for inertial performance. The implementation of the interferometric type of FOG, fiber optic gyros, is best explained in a series of stages, starting with the simple basic system shown in this figure. What we can see here, light from the laser diode source is passed through a first beam splitter and single optical mode is selected. The light passes through a second beam splitter and propagates in both directions around the fiber coil. In the absence of rotation, as already explained, the transit times are identical, and so that when the light arrives back at the second beam splitter, perfect constructive interference occurs with accompanying fringe pattern. The gyro output signal is obtained by directing the returning light via the third beam splitter to a photodetector. As explained, an input rotation rate about an axis normal to the plane of the coil results in a difference in the transit time between the clockwise and anti-clockwise beams as given by first equation here in this slide. This equation, as you remember, delta T proportional for A over C squared times theta dot. If the fiber coils has n turns, in this case, A proportional pi r squared times n, where r is the mean radius of the coil, and n capital here in this expression can be expressed in terms of the length of the coil, L, and the mean radius r. In this case, we may found next expression here, n proportional L over 2 pi times r, and hence delta T proportional LD over C squared times theta dot. D here is the coil diameter, or simply equals double radius to r, right? Nice. This transit time difference results in the Sagnac phase shift given by these first expressions. F sub s equal omega times delta T. Omega here is the angular frequency of the laser source and proportional to pi c over lambda. And lambda is the laser wavelength. Very simple, right? And hence, we have F sub c in this expression proportional to pi LD over LC times theta dot. And this phase shift between the clockwise and anti-clockwise traveling light waves results in a reduction in the intensity of the light at the detector. This change in intensity is very small for useful rotation rate and has required the development of special techniques. For example, a typical FOG with an optical path length equal 200 meters, coil diameter 70 millimeters, and source laser wavelength 1.1.3 micron, when subjected to an input rate of 10 degrees per second, we'll have a Sagnac phase shift of this one and get as approximately 2.26 degrees. You know that resolution of dose rate equal 15 degrees per hour, right? Requires the measurement of a phase shift of 3.38 arc seconds. resolution of 0.01 degrees per hour seems very credible at first sight, but it's achievable, as will be shown. The next problem to be overcome with the simple interferometer shown in this figure is that the relationship of the intensity of the fringe pattern to the Sagnac phase shift, which is proportional to the input rate, is a 1 plus cosine law, right? And this results in a minimum sensitivity at low input rate, and it is thus necessary to introduce a phase shift of 90 degrees, so that the sensor is operating in the region of maximum sensitivity. The technique generally used is an alternating phase bias modulation method, whereby a phase modulator is placed at the end of the fiber loop, as shown in this slide, on the left part of it. The two counter-propagating waves receive the same phase modulation, but at different times. Clockwise wave at the end of the transit route around the coil, and anti-clockwise wave at the beginning of the transit. The phase modulator is driven at a frequency such that half a cycle corresponds to the time delay for the light to travel around the coil. For example, for a 200-meter FOG, this is a modulation frequency about 500 kilohertz. A non-reciprocal modulation, it does produce, another say, a modulation which affects the clockwise direction of propagation differently from the anti-clockwise direction of propagation. Application of an input rotation results in modulated output signal whose amplitude is proportional to the input rate, as you can see on the right part of this slide. And this improved system, as it stands, is an open loop system which with attendant disadvantages such as first, output stability and scale factor is dependent on the stability of the gain of the variation amplifiers preceding the demodulator. The demodulator stability and the stability of the intensity of the laser light source. And second, the nonlinear output characteristic with the phase shift resulting from the large input rate. Output characteristics, usually you remember, is sinusoidal. The inherent limitations on scale factor stability are overcome by closed loop control, shown in concept in this slide. The output of the demodulator is passed through a servo amplifier, which then drives a non-reciprocal phase transducer placed within the fiber interferometer. In this way, the sensor is always operated at null by generating a suitable non-reciprocal phase shift, which is made equal and opposite to that generated by the input rate by action of the closed loop. The output of the system is then the output of the non-reciprocal phase transducer. Next figure in this slide shows a widely used basic architecture for a typical closed loop IFOG. This uses a multifunctional integrated optics chip for polarization, beam splitting the light into clockwise and anti-clockwise waves and phase modulation. The light intensity output signal from the photodetector is converted to a digital value by A to D. A to D converter followed by a digital demodulation and integration. The loop is closed by driving the integrated optic phase modulator with a voltage ramp whose slope is propagated proportional to the input rate. This ramp produces a non-reciprocal phase shift between the light waves so as to restore and maintain the sensor at the zero rotation condition. The advantages of the closed-loop system are: first, output is independent of light source intensity variations, as the system is always operated at noon. Second, output is independent of the gains of individual components in the measurement system, as long as very high open-loop gain is maintained. And last, output linearity and stability depends only the phase transducer. The voltage ramp driving the phase modulator generates a frequency difference to null the phase difference produced by the input rate. Frequency difference and phase shift are directly related. The phase shift F capital that light experiences is propagated along a single mode optical fiber of length L capital in the nominator here you see, and reflective index M is given by this expression. F here is the frequency of the light, I hope you remember, and velocity of propagation of the fiber proportional C over M. Okay? Hence, dF will be proportional the same as the coefficient 2 pi NL over C times dF. And Sandiak phase shift will be explained as this expression, 2 pi LD lambda C times theta dot. And hence, at noon, we can get this expression, 2 pi NL over C times delta F will be equal as 2 pi LD over LC times theta dot. Here we have the K1 as a D over NL. The output characteristic is thus the same as the RRLG, and the IFOG behaves as the integrating rate gyro. The scale factor stability is dependent on the stability of D capital, M, and lambda. For example, FOG already used D capital 70 millimeters, lambda 1.3 millimeters, M 1.5, and after substituting these values, one output pulse corresponds to an angular increment of 5.75 arcseconds. So this equation can be shown to be the same as the RLG output equation by multiplying the numerator and denominator by pi d capital over 4. And exactly we can get as this last expression here. Delta F proportional d capital over n lambda times pi d over 4 divided by the pi d capital over 4 times the theta dot. And after transformation, we can get very simple expression for A over lambda n pi d capital times theta dot. The equivalent optical perimeter, it's usually NPD capital, corresponds to the RLG path length L capital. The inherent simplicity of the FOG and the use of integrated optical chips, where the various electro-optical elements are integrated onto a substrate, leads to low manufacturing costs, and the IFOG is a highly competitive gyro in terms of cost, reliability, ruggedness, and performance. Integrated three-axis versions are being produced with the three FOGs sharing the same laser diode source. This figure is a photograph of the prototype of the inertial measuring unit, IMU of the fiber optic gyro-based attitude heating reference system, developed by the US subsidiary of the former Smiths Industries in the UK. The mechanical simplicity of an IFOG can be appreciated from the photo. Basically, a few hundred meters of the single-mode optical fiber wound on a spool. The sophistication resides in the electro-optical devices and the processing chips. The IMU incorporates 3 interferometric fiber optic gyros and 3 accelerometers. The 3 FOGs share the same laser source. The FOG triad system is configured to share many of the optical and electrical components between the 3 FOG axes by time sequencing the processing of the optical signal for each axis using optical switches. By time sharing components, the cost, weight, and volume are significantly reduced while reliability is increased by reducing the number of parts. The optical switches also replace the conventional beam splitters and increase the signal to the noise ratio in the detected signal. The fiber coils of the gyro are comprised of 400 meters of non-polarization preserving single-mode optical fiber wound on a 3.5 centimeter diameter. The quoted gyro performance is 0.8 degrees per hour, or only 1 sigma. Scale factor accuracy 60 ppm or 1 sigma, and random walk 0.04 degrees per hour. The IMU weighs 420 grams and is 245 cubic centimeters in volume. Power consumption only 7.5 watts. The major improvement in all aspects compared with the previous gimbal AHRS units using angular momentum gyros can be appreciated, right? To achieve inertial quality performance has required particular attention to minimizing non-reciprocal optical error sources such as polarization. Detailed discussion on these error sources and methods of minimizing their effect is beyond the scope of our lecture. And some of you who asked to accept their resolution as a fact. The effect of environmental noise sources must also be minimized in a FOG design in order to achieve inertial quality performance. This is because these non-reciprocal effects introduce would otherwise swamp the small Sagnac phase shift being measured. Environmental noise sources include temperature variation. Operation environments can range from -40 to +70 centigrade, with ramp rates of half to 1 centigrade over minute. Acoustic noise, in this case, optical fiber, is acoustically sensitive to the sound pressure. And in fact, fiber optic sensors are widely used in sonar arrays because of the sensitivity. Mechanical vibration, introducing mechanical stresses in the fiber with accompanying non-reciprocal effects. Environments of 6 to 9 G can be experienced. Magnetic fields, a magnetic field acting parallel to the optical fiber, results in a Faraday rotation of the state of polarization in the fiber. This is a non-reciprocal effect, which results in an unwanted phase shift. Fluctuating magnetic fields of up to 10 gauss can be experienced about any axis. New metal magnetic screening will almost certainly be necessary. Very high inertial accuracy performance has been achieved by the several manufacturers of closed-loop IFOGs using polarization maintained optical fiber in the sensing coil and production status achieved. In a paper published more than 20 years ago, Honeywell reported very encouraging progress using depolarized fiber in conjunction with polarization randomization in the loop. Depolarized fiber is widely used in the telecommunications industry and is of much lower cost than polarization maintained optical fiber. A Honeywell brochure produced in the earliest of millennium for an IFOG-based inertial reference system for space and strategic applications towards a bias stability less than 0.303 degrees per hour. Average random walk 3 times less. Scale factor stability less than 1 ppm for short term. It is worth discussing briefly the relative merits of inertial IFOG and the RLG. The RLG is a very reliable, very well proven, we may say around 30 years operating experience, meets the accuracy requirements and has over 90% or even more of the aviation INS market at the present time. There is no incentive to change such a well-established and highly reliable system at the moment. Its manufacture, however, involves very precise machining operations and exceptionally high-quality mirrors. The IFOG does not require the precision machining processes involved with the RLG, and it exploits relatively low-cost integrated chips. Time alone will tell which type of gyro will achieve the largest share of the aviation INS market in the future. It should be pointed out, however, that there are no low-cost inertial accuracy gyros, irrespective of the technology. This is because of the extreme accuracy required from them. Some cost less than others, but they still do not come cheaply. Another part of today's lecture is accelerometer. We will be continuing into a bit later, okay? Let's stop it for these. Let's stop. I want to